Last time, we talked about fusion as a nuclear reaction, how deuterium and tritium can fuse together to release energy. But before we talk about things like magnetic confinement, we need to actually understand what we're trying to control at the center of the reactor, the plasma. Today we're going to talk about the plasma physics you need to know to talk about fusion with more nuance. Here's Plasma 101, the fuel of fusion. At the most basic level, plasma is an ionized gas. In an ordinary gas, atoms are mostly neutral. The electrons are still bound to the atoms, so the gas behaves like a collection of neutral particles. But if you add a lot of energy, some of those electrons can separate from their atoms. Now, instead of only neutral atoms, you have ions and electrons moving around separately. That ionized gas is a plasma. But saying plasma is free electrons and ions is only the beginning. Once the particles are charged, the electric fields start to matter. So you may think, if the whole plasma is filled with charged particles, does the plasma have a net charge? Actually, in most fusion plasmas, most of the charges cancel each other out. The electrons are negative and the ions are positive. And over a large enough distance, the net charge is close to zero. This is called quasi-neutrality, meaning almost neutral. But the almost is important. While charges mostly bounce, local charge separations are where a lot of the plasma physics actually happens. One of the first examples of this is Debye shielding. Let's say we place a positive charge inside a plasma. The negative electrons are attracted to it, while the positive ions are repelled from it, reducing or screening the electric field over a short distance. This is Debye shielding, and the distance over which this happens is called the Debye length. It tells us the scale where individual fields get screened out by the plasma. If you're looking at distances much larger than the Debye length, the plasma does not behave like a bunch of independent charged particles. It behaves collectively. And that's the next big idea. Plasma is collective. Debye shielding is one of the examples of collective behavior, but is not the only one. Because electrons are much lighter than ions, they can respond much more quickly. If the electrons are displaced slightly from the ions, an electric field pulls them back. This creates a natural oscillation called the electron plasma frequency. This means plasma is not static, as someone might think after learning about Debye shielding. It can oscillate, support waves, and develop instabilities. Later on, when we're talking about heating up the plasma and controlling it, this becomes really important. So far, we've talked about charge. But for fusion, another major important part is energy. How fast these particles are moving. In most science, we measure things in Celsius or Kelvin, because that scale makes sense for the experiments. But in plasma physics, and especially in fusion, temperature is often measured in electron volts or EV. This is because temperature at this scale really means average kinetic energy per particle. 1 electron volt corresponds to a whopping 11,600 Kelvin. Fusion plasma is roughly around 10 kiloelectron volts, or 100 million Kelvin. As we talked about it last week, these temperatures are necessary to overcome the electrostatic force in the Coulomb barrier to achieve fusion. Since nuclei repel each other electrically, having higher kinetic energy increases the chances of a fusion reaction. Importantly though, not every particle in the plasma has the same kinetic energy. The particles have a distribution of speeds and energies. The basic starting point for this is called the Maxwellian distribution. As temperature increases, more particles reach the high energy range where fusion is likely. Now we have the two main ingredients. Plasma is charged, and particles have incredibly high kinetic energy. The next question is, what happens when these particles enter electric or magnetic fields? In a single charged particle, the Lorentz force governs its motion. Here's the equation. This explains how electric and magnetic fields exert forces on charged particles. Electric fields push charges along or against the field lines, depending on the sign of the charge. Magnetic fields are different. A magnetic field bends the path of a moving charged particle. The magnetic force acts sideways to the particle's motion, which causes the particle to curve instead of moving in a straight line. This spiral motion is called Larmor motion or gyro motion, and the radius of that spiral is called the Larmor radius or gyro radius. Here's the equation. And this tells us a few important things. A stronger magnetic field means a tighter spiral. A heavier particle has a larger spiral. And a faster particle, specifically faster motion perpendicular to the magnetic field, also has a larger spiral. This is one of the key ideas of magnetic confinement. Charged particles have a much harder time moving across magnetic fields than going with them. So if we can design a magnetic field in the right shape, maybe we can guide and confine the plasma without letting it touch the reactor wall. But here's the catch. A fusion plasma is not just one charged particle. It's an enormous number of electrons and ions interacting with each other and exhibiting all of the complex concepts we just covered. That's why it's helpful to sometimes describe plasma in different ways. Sometimes it's helpful to talk about it in terms of individual particles. This is useful for ideas like Larmor motion, collisions, and high energy particles. Other times we treat plasma more like a fluid. This is useful for large scale motion, pressure, waves, and instabilities. There are other framings too, depending on the problem. That's why plasma, and therefore fusion, is quite complicated. It's not just a one particle problem. It's a many particle collective electromagnetic system, and we need different models to understand different parts of it. So let's review the main ideas. Fusion plasma is ionized. Electrons and ions move separately. It is quasi-neutral. Positive and negative charges mostly balance, but local charge separation still matters. It's collective. The plasma shields, oscillates, supports waves, and responds as a system. And it's magnetized. Charged particles spiral around magnetic field lines. These four ideas are the foundation for the rest of the series. But now that we know that electric particles spiral around magnetic field lines, the next question is obvious. Can we use magnetic fields to trap plasma? That's what we'll talk about next week. Magnetic confinement, tokamaks, and stellarators. And here's what else I'll be covering for the next few weeks. The next video will also be linked here once it's out. Feel free to leave any questions down in the comments, and please drop a like and subscribe while you're down there. Anyway, why are you still here? Go learn about stellarators.